The law of reflection is a law that you've seen a million times before, whether you play pool, okay, or whether you have seen waves reflect off of something or shine a light off of a mirror. You've seen the law of reflection take place. It says the angle of incidence. We know what the angle of incidence is, right? We've talked about refraction. The angle of incidence is that ray of light that strikes the boundary, or the angle of the ray of light that strikes the boundary with the normal line. This would be our angle of incidence. Theta 1, we'd call it right there. Well, if the light reflects, then we know that the angle of incidence will be equal to the angle of reflection. If you hit a pool ball off the bumper of the pool table at this angle, theta 1, then it's going to bounce off the bumper of that pool table at theta 2. The angle of incidence will equal the angle of reflection. Theta 1 will equal theta 2. That's the law of reflection. Now, we're not going to focus on that a whole lot. We're going to do a couple real quick examples using the law of reflection as it's written right here. But we're going to focus more on curved mirrors, like we did on curved lenses. But understand that when we do curved mirrors, the law of reflection still holds. The angle of incidence still has to equal the angle of reflection. When we did lenses, the base concept was refraction. When we're dealing with curved mirrors, the base concept is reflection. Here's a couple real quick examples, lightning fast examples here. Okay, first ray of light here, it strikes a boundary at 48 degrees. It's going to bounce off over here somewhere, right? What's the angle that it bounces off at? You better get this one. 48 degrees. Okay, that is maybe the world's easiest physics question. The angle of incidence equals the angle of reflection. Just be careful that you don't label this angle right there. It's always measured from the normal line, not from the boundary. All right, this one's a little bit harder. Let's assume that this is 90 degrees. It should say that, but let's assume that it's 90 degrees. The first ray of light bounces off the first mirror, and then it hits the second mirror, and then it bounces off the second mirror. What's the angle of reflection off of the second mirror here? We'll call this one theta 4, right? Theta 2, theta 3, and then theta 4. What's the value of theta 4? What's the value of theta 2? $55 degrees. What's the value of theta 3? Ooh, that's a tough one. What is it? 55? Half of it? 7? Not Pythagorean theorem, no. But you're, yeah. If this is 55 degrees, then this angle would be 35, right? Because the normal line is always drawn at 90 degrees. So 55 and 35 gives me 90 degrees. And this is 35, and this is 90, then this would be 55. And if this is 55, then this has got to be 35. So theta 3 will be 35 degrees. Does that make sense? Some of the angles inside that triangle has to add up to be 180 degrees. We know that we've got 35, 90. This one, therefore, has to be 55. And if this is 90, because the normal line is always drawn perpendicular to the boundary, if this is 90 and this is 55, then this one's going to be 35 degrees. All right, then what's theta 4? Now it's an easy question. What's theta 4? $35. So that's what we're looking for, 35 degrees here. That's a bit trickier. I mean, the first question we had, easy. Second question we had, the basic concept is easy. But the geometry involved there makes it a little bit tricky, okay? If you got a 90-degree angle, it doesn't matter if you have a 90-degree angle. The sum of the angles inside a triangle have to give me 180, okay? Use that principle if you have to in order to find the angle of reflection when it bounces off of two mirrors. Honestly, I'm not anticipating you're going to get a question like this or like this on your test or on your exam. But we're going to be ready for it just in case. Okay? Just in case. Sometimes we're surprised by things. Okay? We don't want to be really surprised by this. Let's talk about curved mirrors now. There are, just like with lenses, two types of mirrors. Two types of curved mirrors, that is. There's concave and there's convex. But notice the difference here. For lenses, concave, we're diverging. For mirrors, concave are converging. For lenses, convex or converging. For mirrors, convex are diverging. This is a converging lens, a concave lens. If we're looking at it as a cross section, it looks something like this, thinner in the middle than it is at the edges. You guys have all seen this in a fun house before or somewhere, right? Look even in the front of a spoon. You see a concave or a converging mirror. Look at what the image of this guy is when he looks inside this converging mirror. His face is massive, bigger, way bigger, and right side up. Although it does depend upon where he stands, what the characteristics of that image will be, just like it did with lenses. For a diverging mirror, you guys have seen these a million times before. You go to the pool. The pool in Okotoks, they have a diverging mirror, a big bulged out mirror at the corner of the hot tub. They used to have them in stores all the time, in convenience stores all the time. Now they have video cameras. They used to have these as surveillance things, basically. So the guy behind the counter could see the entire store. Notice that the image produced in the convex or the diverging mirror is smaller, way smaller. We can see this parking lot in here with an entire person standing there. So the image is clearly smaller, but upright. Okay, the advantage of that when you got out of the hot tub at the pool in Okotoks is the lifeguard walking by doesn't necessarily have to be able to physically see the entire hot tub. He or she can look up at this mirror and see the entire hot tub in the mirror, in the convex mirror. The advantage at the corner store would have been, again, the guy behind the counter is able to look up at the corner where the convex mirror is and see the entire store, albeit smaller, but still the entire store. So you can see if anybody's trying to steal cigarettes or something like that. So two types of mirrors, convex and concave, but they're reversed when they're converging and when they're diverging. Right, Devin? Once again, we've got some things to label here. The first thing that we're going to label is the principal axis, just the same as it was for lenses, the principal axis. This point right here will be called the focal point. This point right here will be twice the focal point, just like it was with lenses, except that for mirrors, it has a little bit more significance, more than just a spacer. For mirrors, 2F is the center of the mirror, the center of curvature of the mirror. It would be the radius of the mirror. If you made a complete circle out of this mirror, 2F would be smack in the middle of that circle. So when you have a curved mirror like this, a concave or a converging mirror, the focal point will be 1/2 of the radius of the mirror, or 1/4 of the diameter. We don't label the optical center here because with lenses, the rays of light went right through it. With mirrors, of course, they reflect off of it. Now, a little bit harder ray diagrams, marginally harder, because there are 3 rays now. There's millions of rays, but there are 3 that we sometimes have to draw. The good news is we only ever have to draw 2 at once. We just have to pick which 2 we draw. Sometimes the first one and the second one work. Sometimes the first one and the third one work for us. So let me tell you what those rays are. The first ray, if I draw my object way out here, somewhere beyond twice the focal length or somewhere beyond the radius of this mirror, the first ray is going to reflect off of the top of the object, and it's going to go parallel to the principal axis, just like I did with lenses. So easy so far. It's going to reflect. It's not going to refract like it did for the lens. It's not going to go down there. It's not going to go up there like it did for the lens because it doesn't go through the mirror. Where do you think it's going to go? Down this way, down through the focal point. The second one, not quite as easy maybe as it was for lenses, but the second option that I have here is to go from the top of the object down through the focal point. Where do you think it's going to go? Physics is a subject of symmetry. When A happens, when A causes B, then B will often cause A. If parallel to the principal axis goes through the focal point, then going through the focal point will end up going parallel to the principal axis. So this ray will reflect parallel to the principal axis, like this. Where do the reflected rays intersect? Right here. Right here. There are three characteristics of that image. Number one, it's smaller. Number two, it's inverted. It's flipped upside down. And number three, it's real. Because it's solid lines that intersect. Now, it may seem odd to be able to say you're standing right here where this object is, to be able to put a piece of paper right here and actually see a projection of yourself on that piece of paper. It may seem odd to be able to do that, but you can. As long as you put that piece of paper or that screen below the principal axis, you would see an image of yourself. Now, you could also see the image of yourself by looking into the mirror, but you don't have to look into the mirror. You can project it onto the screen. Just like we did with the lens here yesterday or the day before, pointing it at the condos. Let's try our second one. Our second scenario is when we have our object at the radius or the center of curvature, or 2F. First ray is going to go parallel to the principal axis down to the focal point. Second ray down through the focal point and parallel to the principal axis. Okay, there's something off with my diagram here with my mirror, and I'm not sure if you guys are going to encounter that situation with a template that I handed out or not. Okay. If I draw this perfectly and my mirror is drawn perfectly, which in this case it's not, it should have actually been formed directly below the object. So fudge it if you have to on your diagram so that you recognize that it is directly below the object. The characteristics of this one would be that it is same size. Let's just finish this one off and then we'll back it up here. Same size. It's inverted. And once again, it's real.
Kate Friesen, Gallon Johnson, in front office, please.
What's your homework for tonight? Worksheet number 19 or 18? 18, yeah. And this question's 1 to 3 practice problems, right? Have a good night, everyone.